just said. So what we just said was first up, class today until 7. Okay. A full class on Monday, review. And then when you leave on Monday, you'll walk out with the exam 3. Take home. And you'll turn it in on Wednesday at the beginning of class. That'll be our last day of class, and then you'll be able to, to talk about it as, after the fact, after you turn it in, if there's something that really troubled you or something like that. Any last minute kind of loose ends, we'll take care of those on Wednesday. And then final exam is the following week. Okay. But what we'll do before that, if you need it, we'll say that Monday is a reading day officially, but we'll just continue on like as if there was class. It'll be a review session. During normal class time, optional of course. Sorry, this thing is delayed. It's really weird. Okay, any other questions? Do you have any questions about the logistics there? Is that clear? Okay. All right, great. So where are we? We were in 16.3, talking about how to deal with line integrals in a better way than just parameterizing the curve. We said if it turns out that you have an exact differential or the vector field is the gradient of some function, then you can instead use the fundamental theorem of line integrals, and you could find out what that function is, and you just evaluate that function. Or you can pick a convenient path and evaluate that line integral. So we did a few just straightforward. This is not what I wanted. I added a slide in here somewhere where we did this problem using the potential function. It's gone for some reason, but I think I uploaded it. Did I upload the 16.3 notes? Yeah. I think it's on the upload. Here's the extra slide. It's on there. I apologize about this projector. It's really upsetting me. But anyway, so then we went through and worked out an example or two. We did it and used the fundamental theorem of line integrals for it. And we said that you don't always have to do it this way. There's an option for you. And it's a really good option when you can trade your path in for some other path, especially a horizontal path. So our convenient path, it's not written on here for some reason, but it's the path that connects along the x-axis 2 to -2. It should be written on there. And so I think that's about where we stopped at. And we did add that extra slide on there at the end. So what am I, here we go. This path here. That's very convenient because y is 0, so dy is 0. So that kills that whole part there. You don't even care about that. And it turns into a simple Calc 1 integral at that point. So be on the lookout for that. When you can just recognize that you are independent of path and you get to pick a convenient path. And then we ended last class with this notion of, okay, well, what if you are independent of path, but you're closed at the same time? Then the fundamental theorem of line integral, we're supposed to do phi of the ending point minus phi of the starting point, but the ending point and the starting point are the same. You know, it's just going to zero out. I'm going to put this all together in a nice flow chart in a second. So we actually finished 16.3 last time. Do you guys have any questions? We just have to cover 16.4, and then I'll give you a flow chart, and we'll begin basically our review. And remember that at 7 o'clock we need to stop. Okay, if you came in late, these are some notes that you need to know. Class ends at 7 today. Full class on Monday. We'll be reviewing for exam 3. You'll leave on Monday with the exam 3 in your hand as a take-home. You'll have a 48-hour window, or I guess a little bit less than 48 hours, to turn it in at the beginning of class. And I'll enforce that by, I don't know, taking off a point for every minute that you're late. How's that sound? I don't know. And then we'll have a full class that day. And then you can, ask me questions. We can review. We normally would have a class the next Monday, but it's reading day. But I'll be around. I'm trying to book this room. And then the exam is on the 12th. Okay, so 16.4, and then we have this nice flow chart that's going to hopefully get all the different ideas together about what to do with line integrals. Okay, if you take 240, what 240 does is they cover this material really quickly, maybe in like one lecture. All of this chapter 16, 1 through 4, they cover really quickly because they expect you to have it in 114, and then they take it to the next level. Basically, Green's theorem is a two-dimensional theorem, but all of these things could be, these vector fields, they could be 3D. And so what happens is they take it to another level. They introduce something called a surface integral, and they do the other two classical theorems in vector calculus are called Stokes' theorem and the divergence theorem. And they'll be in 240. So it's weird. We're going to build up and then stop short, and then 240 is going to pick up if you have to take 240. All right. There's a new symbol that we haven't used before. The integral symbol has a circle on it. That's to indicate extra that the curve is closed. Okay. It doesn't have to be there. It's just an extra indication. So if you see it, it means the curve is closed. But it can be explained to you in the description of the curve that it's closed. But just so if I just want you to know what that symbol means. When you have a closed curve, there's a certain orientation we want to talk about. If you can traverse along the curve in a manner so that as you do it, your left hand is pointing to the interior, then that's called a positive orientation. It's counterclockwise. But if you traverse along the curve in the other way, then that's a negative orientation. Okay, so counterclockwise is desirable. Counterclockwise is positive orientation. And clockwise is a negative orientation. We would like to have counterclockwise. But we've seen that if we just need to reverse the orientation, we just put a negative out front. And so sometimes they even go a step further with the notation. This is extra, too much extra. The circle itself is extra, but now this guy here with the circle plus the orientation of it, it's really extra. But if you see it, I want you to know what it is. that's a counterclockwise orientation of the circle on the integral symbol. So they're telling you the curve is traversed counterclockwise. They're telling you that in the symbol. And then this other symbol, the clockwise circle, and it's the opposite of the other one, that's all. Right? If you want to switch the orientation, you just got to put a minus and do it the other way. Just like you did kind of when you had a regular Calc 1 integral that was kind of backwards. You just flip it around and put a negative out front. Okay? All right, we need this because part of Green's theorem demands that the curve is counterclockwise. And, well, of course, closed. All right? So here's what it says. Some people call Stokes' theorem the 3D version of Green's theorem. Anyway, here's what it says. Here's what you need. You need your curve to be the following. We said it. Positively oriented, closed, simple means it doesn't cross over itself. Maybe it's not smooth as you know, without sharp points, but maybe in pieces it's smooth, piecewise smooth. Okay, and closed. And if that's the case, then there'll be some interior region, right? If your curve is closed, there's an interior region. And here's what Green's theorem says. You know what? This line integral that you have, you know, based off of this curve, if it's true that the vector field P and Q is such that when you take these partials, they exist, they're continuous and everything, then here's what you can do. You can trade the line integral in for a double integral. That's what Green's theorem says. It says that line integral can be traded in for a double integral. The double integral will be basically over the interior region. You got this interior region we call R, and so we'll go back to the beginning of double integration. We'll go back to chapter 15, and we'll be doing double integrals. The integrand, the thing that's in the integral, is the difference between the x partial on P and the y partial on Q. The same kind of things that you do to check to see if you're independent of path. When these are equal, right, that's a 0. And you'll be independent of path. And just like we had said in our intuition, that if the thing is closed and you're independent of path, the line integral should be 0. And this is an indication of that because qx minus py will be 0. So the integrand will be your x partial on Q minus your y partial on P. And it's not always true that you're going to be trading in a line integral for a double integral in that direction. It's possible to trade the double integral in for the line integral, but that's maybe like 5–10% of the time. Most of the time, you'll be going from line integral to double integral. And what's really nice is when the qx minus py is a constant. Because think about what that means. Say qx minus py was 5, right? You could take that 5 and pull it outside. And then what is this symbol? If I take this thing that's in the parentheses, right, and it's a constant, and I pull it outside, the symbol that I have left is double integral dA. What's that called? The integrand in that case is a 1. It's the area of that region. So it really turns into, most of Green's theorem problems turn into that, where qx minus py is a constant. You pull it out, and you just end up finding the area of some 2D region. Okay, we'll see some examples of it. And you have some on that homework 6 that I just put up. Okay, this one isn't that, though. So here's our first example. Y squared dx plus 3xy dy. And the curve is going to be this ridiculous-looking curve here. Okay? No way are you supposed to parameterize this in parts and plug in and do it from the way we did it back in 16.2 or 16.1. No way it's supposed to be done that way. Okay? Instead, you recognize that it's a closed curve. It's piecewise smooth. It's simple. And it's positively oriented. So we're going to use Green's theorem and trade it in for the double integral over that donut region. The fact that it's a donut region is screaming to you that, okay, yes, it's a double integral, but you don't have to do it in terms of x and y just because it's a double integral. We've done double integrals in polar. We had a whole section on double integrals in polar. That's what this is going to turn into, a double integral in polar. or it'll be the area between, basically the region will be the region between these two circles, concentric circles, centered at the origin of 1 and 2. Okay. So what's the double integral you trade in for? You have to take the y partial on P and the x partial on Q, and you have to subtract them. So what is it? What is the x partial on Q? 3y. We'll start with that. And from that, you're to subtract the y partial on P. 2y. Oh, that's convenient. When you subtract them, you get y. That's your integrand. And we announced that we're using Green's theorem by putting this GTHM above the equals. You don't have to do that. All right. So now I went from 16.4, now I'm in 15.4. I have to do a double integral in polar. What's my bounds on R? Where does R go from? 1 to 2. Remember how this works for double integrals in polar. It works where you swing this guy for positive theta, and the R bounds would be 1 to 2, R equals 1, R equals 2, and the theta bounds would be 0 to pi. But don't forget though, there's other action going on. Yes, those are the bounds. But what about this junk? What does dA become? Yeah, I can't forget that R. R is critical. R, dr, d theta. Okay. And then Y is going to have to turn into R sine theta. Okay, so that's all the... And so Y becomes R sine theta. dA becomes R dr d theta. The double integral is R goes from 1 to 2 and theta goes from 0 to pi. You're on your way. Okay, there, you are not meant to parameterize this. It's not independent of path. This is the route that you have to take. This is the way to go to get this problem. Okay, put the r's together, call it r squared. Integrate r squared from 1 to 2. R cubed over 3 from 1 to 2. That's a third of 8 minus 1. That's 7/3. Great. And then that's the interior. Now you're integrating from 0 to pi. Take that 7/3 out. You're doing sine of theta d theta. What function has sine of theta as its derivative? Negative cosine. Very important. Okay. From 0 to pi. Just be careful with the signs here. Don't forget the 7/3 on the outside. Okay. Pi. Cosine of pi is already -1. This negative turns it to be +1. Upper limit. Lower limit would be cosine of 0, 0, which is itself 1. This negative makes it -1. The negative from integration makes that plus, so we get a 2 out of that. With the 7/3, the final answer is 14/3, and really there's no other way to do it. So the navigation of how do I know? Do I do it the way back in 16.1 with parameterizing? Do I do it by trying to see if it's independent of path? Do I make my own path? Do I do Green's theorem at the end of class today, which is going to be in 20 minutes? I'm going to give you a flow chart, and this thing is like gold. This flow chart is gold. You'll love it. It'll tell you how to navigate that mess. Yes?
Will you give us the picture of the
Well, maybe. You can do it, right? If I say the end, yeah. What? Possibly, yeah. Yeah.
What did you mean by precise
smoothing parts. If you were to parameterize this, you have to break it into parts. Those parts are smooth.
Smooth as in.
Not sharp.
Okay.
Differentiable.
And positively oriented, you mean
Counterclockwise.
But isn't that inner circle clockwise? The inner part? What's going on there?
If this was like down below, it would be like, you know what I mean? It really is. As you go, that really is. Remember what it means. As you walk along, your left hand is pointing towards the interior. It is positively oriented. I know it looks like it's clockwise, that part is, but it's not though. Because the interior is to your left. Let's walk, let's walk, let's walk. Here we go. You're walking, and then you do the circle part, and then you do this part. The interior is always in your left. It is positive. Although that thing looked kind of like, it's the fact that the interior is not the part of the circle inside. The interior is that part, outside. So it's okay. It is positively oriented. Yeah. Okay. Okay, great. Yeah.
If we had been given that picture, how would we have found the balance on the bar?
It had to be some great explanation to get you from the explanation to that picture. You know, the region between the circle of radius 1 and radius 2, centered at the origin, with positive values, the semicircles. I don't know. I'd have to come up with some great explanation if I don't give you the picture.
Okay.
And then from there, figure out what's going on. Here's another. When your integrand looks messy like this does, messy as in functions that will give you trouble if you actually try to integrate them, then it's an indication that you definitely are not going to do this by parameterizing the curve. You'll be wasting your time trying to parameterize the curve. Here's the curve. It's between, it's that one we had before. Go from the origin up to 1, 1 along the curve y equals x squared. Then go back to the origin along the curve y equals root x. We had that one before. It was closed back then. We just didn't know what was going on there. Positively oriented. And we want the line integral of that function over that. Remember how we had to do two different parts? I mean, it's not bad to come up with the parameterization, but when it comes time to do all the substitutions, you're not going to be able to integrate that. But not with an e to the root x and a cosine of y squared. You're not going to be able to do it. So the moral of the story is to do the y partial of p and the x partial of q. X partial of q first. What is the x partial of q? Qx is 2. What is the y partial of p? Y partial. That whole e root x, that's constant. Okay, and you subtract them. You get 1. When you get a constant, that's really nice. Especially when the constant is 1. That's just great. Trade this in for a double integral over the interior, where qx minus py is a 1. And that's more commonly known as the area of the region. Be on the lookout for that. That happens a lot with Green's theory. Okay, let's trade this in, not for a double integral. Let's go back to Calc 1. If I want to find the area between curves, upper curve minus lower curve. So let's trade this into, we went from line integral to double integral, now to single Calc 1 integral, upper curve minus lower curve from 0 to 1. We could have set up the double integral, and the first thing would have been us doing exactly that, upper curve minus lower curve after integrating the first, function 1. It's just best to do it this way. Okay, x to the half, antiderivative is x to the 3/2 times 2/3. X squared antiderivative, x cubed over 3. Minus, evaluate it from 0 to 1. That's the area of that region. 1/3. Done. So it's a gift when qx minus py is constant. Take the gift and be done. Questions? All right. So we have to teach you how to navigate the whole line integral by parameterizing, integrating a path, Green's theorem, make my own path. We'll go over how to do that with the flow chart. Example 3. Okay, the picture won't be there this time. They give you a description of the curve, and they tell you that it's positively oriented. How do they tell you that it's positively oriented? By this weird symbol here. Okay, so then you put the curve together, you put the picture together. Pictures are necessary because you're trading this in for a double integral, and we know that pictures are necessary for a double integral. Okay, P and Q, P and Q, P and Q. You're supposed to take the x partial on P. Thank God you don't have to take the x. Thank God you don't have to take the x partial on P. You have to take the x partial on Q. What is the x partial on Q? Ooh, what's arctan's derivative? Arctan. 1 over 1 plus. Okay. So in this case, and the 2 goes along for the ride. All right, that's Q sub x. And P sub y, there are no y's in P. P sub y is 0. Okay, so Qx minus Py, the integrand in the double integral that you're supposed to be integrating over, is just 2 over 1 plus x squared. Okay, this is going to be polar. This is going to be just an x and y integral. Your choice. Do you want to do it dy dx, or do you want to do it dx dy? Dy dx? That's what you thought of first? Let's go with that. Dy dx is a vertical rectangle moved horizontally to cover up your region. Your inner bounds are based off of y equals to y equals. The low bound is this curve. What's this curve? What's this line called? Y is negative x, right? This point here is negative 1, 1. This point here is 0, 1. And this point here is your origin. Yeah, that's y equals negative x. That's your lower bound, negative x. What's your upper bound? Y equals 1. Great. Then we're going to do dy first. And then later we'll do dx. Oh, wait. Sorry. What are the bounds on x? Where do you move this from, starting to ending? Negative 1 to 0. Very good. Negative 1 to 0. Okay, this isn't as easy as when you had that nice constant, but it's doable though. Because you're integrating with respect to y first, that whole 2 over 1 plus x squared is a constant. So the antiderivative of that is just that guy times y. As y goes from negative x to 1. So you put a 1 in, and you just get that guy. And you put a negative x in, and you get... But remember, it's upper limit minus lower limit, though. So this negative is going to be a plus. Okay, how are we going to get this guy? Well, the antiderivative of the... Let's take the 2 out. Okay, it's 2... Negative 1 to 0. 1 over 1 plus x squared. Plus x over 1 plus x squared. One guy is just the antiderivative of the one guy is just arctan. What about that? A u sub, and it end up as a natural log. Let u be the entire denominator. Because du is twice x dx. So this x dx will be half of du. So you'll be looking at 1 over u with a half du. So it's half of the natural log of u. Sorry, I'm running out of space here. Let's go to the animation. I'm sorry. Let's go to the animation. My handwriting is just deteriorating here. It's messing it up. Okay. We get the natural log of, let's do it from here. We get, this is the arctan. We're going to pull the 2 out and get the arctan of x. If we pull the 2 out here, we get half of the natural log of 1 plus x squared. Okay, if u is 1 plus x squared du is 2x dx, half of du gets to be the replacement to x dx, so you do half 1 over u du, which is half natural log of u. All this is little side work to help you find out that the antiderivative is exactly that. We gotta plug a 0 in. What is the arctan of 0? 0. What is the natural log of 1? 0. Oh, that's weird. So the upper limit gave us 0. Okay. Lower limit. What is the arctan of negative 1? Be careful. With arctan, you can't give the angle as being the positive angle in that fourth quadrant. It has to be in the fourth quadrant first of all, but it can't be the positive version. It can't be, I think it's 7 pi over 4 in the fourth quadrant. Arctan, you have to give the answer as some angle between minus pi over 2 and pi over 2. Remember the bounds on arctan? So negative pi over 4. And the and the natural log of, I guess it's going to be 2. Just leave it like that. Half log 2. Half log 2, is that what that is? When you square the negative 1, you get a 1. 1 plus 1 is 2. Yeah, half log 2. So this guy's zeroed out. Don't worry about that. And then the minus applies here. And we're talking about, essentially, final answer of 2 times a pi over 4 minus half log 2. Go ahead and put the 2 in. And you're talking about pi over 2 minus the natural log of 2 for your answer. Right, it got a little messy. I mean, it could have been, better, but it's not undoable. You just all of a sudden we're thrust into doing a double integral that might have given you some trouble, but it's not like integration by parts or anything that complicated. It's just recognizing arctan and recognizing the u sub. Would it have been easier if you would have done it dx dy? I don't know. No, you couldn't do it, right? Because you have an arctan of y that you'd have to integrate. No, you couldn't do it. You couldn't do it. Yeah. If you tried, let me just. Okay, no. All right. This might be. This is possible. I don't know for sure. This is possibly one of those 10 that I assigned for homework 6. I'm not sure. Okay. This is exactly how the problem is on the exam, where you get the triangle, just like that last triangle. They tell you it's counterclockwise. It's up to you to get the picture. It's up to you to tell what's P, what's Q. It's up to you to recognize that it's closed, so you can try Green's theorem. And you do Q sub x negative 1, P sub y 1, and you subtract them. And you get a negative 2. And that's great. You like when there's a constant there, because then it becomes the double integral over R, which you can take that constant and pull it out. And you're talking about the area of that region. You don't even have to use calculus. When I gave this on this exam, I was so surprised by how many people try to use calculus to find the area of that triangle. It's a right triangle. Base times height, divide by 2. I mean, you could do double integral dy dx, but why? All right, this is the area of this triangle, 4 by 3. It's a right triangle, so that's 6. 1/2 of base times height. But don't forget the -2. Final answer, -12. And that's really how easy it was supposed to be. Question, yes?
On the last one, how did you know that the arctan of -1 was high?
Yeah. So arctan has a domain of the first and fourth quadrant, and you can't label these fourth quadrant angles as the positive version. You got to label them as the negative version. So the domain of arctan takes on angles that have to be from -π/2 to π/2. Same thing for arcsine. And so you want the angle that when you plug it into tan, you get a -1. That's what arctan of -1 is asking. Go find the angle that when you plug it into tan, you get a -1. And that's why we ended up down here at the 45. Called -π/4. Very good. All right, if you're weak with that, Google my 103 notes and go to inverse trig. I have a section on that with their derivatives. I can't remember what section in the textbook it is, but it's in our same textbook. Okay, great. All right, I can't really do this in 2 minutes, but right, it's what we said. Right. When qx minus py is 1, that's just wonderful. Just go find the area of the region, maybe without calculus, if it's some recognizable shape. All right, and we need to stop there. So those of you who came 10, 15, 20 minutes late, I'm sorry you're only getting 10, 15, 20 minutes of class, but class has to end right now. Okay? And if you came super late, you missed these notes at the beginning. Here's the notes. Let me give them to you one more time. First off, class ends now. Secondly, Monday's class is a review class for exam 3. You have another assignment up, homework 6. So do that. It'll help you for the exam. And I buried the lead. The major point is that the exam take home. So you get to walk out with the exam on Monday. A 2-day turnaround, not like a whole week turnaround. 2-day turnaround. Last day of class, Wednesday the 5th. Turn in that exam at the beginning. Docked 1 point for every minute late. And then we'll have a full class that day, just talking about maybe some things you had issues with that on that exam, but getting you ready for the final exam, just doing a bunch of problems that we haven't done yet. Monday, we'll behave like normal, even though it's a reading day, and we will have class. You can come if you want or not. It'll be a review session. Hopefully, be here. And then final exam is on the following Wednesday the 12th.
To get the full shit.
You want that flow? Oh, you don't want to wait for it? Okay. There's a nice flow chart here. It's gold. You should take it. We'll go over it on